So just before we get started with proving things are divisible by certain quantities by induction, let's just first look at this false theorem. The theorem is all horses are the same colour, which hopefully we know is false, but even so, let's consider the following proof, which is obviously not a real proof. So let's prove it by induction on the number of horses, n. So base case, n is 1. Well, if we only have one horse, it's the same colour as itself, so we're done. Assumption, assume true for all groups of horses of size n, and then consider a group of horses of size k plus 1. Well, then we have, so I'll just draw dots to mean horses because I'm not very good at drawing horses. So for example, consider k is 5, then k plus 1 is 6. So these 6 horses we can split into a group like this of 5. So in this group of 5, they're all the same colour by the assumption, because we assumed it's true for size 5. And we can also consider a different group of size 5, this group. This is also a group of size 5 in red, so all horses in the red group are the same colour. So therefore, all 6 horses are going to be the same colour. So by splitting this k plus 1 into 2 subsets of size k, all horses in a group of size k plus 1 are the same colour. And then we can make the appropriate conclusion. So my question is, where does the proof go wrong? Because obviously it's false. Not every horse is the same colour. So where does it go wrong? And I'm not sure if I want to tell you just yet. Maybe I'll leave it for you to think about. But yeah, that's a really good question to think about, why this doesn't work in this case. So now on to divisibility. So if we want to prove an algebraic expression is divisible by a certain positive integer, then induction is often a good method for doing that. So for example, if we want to prove 3 to the 2n plus 11 is divisible by 4 for n a positive integer. So what do we do first? Well, the first thing is the base case. So if n equals 1, 3 to the 2n plus 11 is 20, which is 5 times 4, so divisible by 4, so it's true for n equals 1. Then we assume 3 to the 2k plus 11 is divisible by 4. We assume it's true for n equals k. And then we show, if we consider 3 to the 2k plus 1 plus 11, we want to show this is divisible by 4. So the idea now is to somehow rewrite this in terms of the previous thing, 3 to the 2k plus 11. So we can split it up as 3 to the 2k plus 2 plus 11, which is 3 to the 2k times 3 squared plus 11, which is 9 times 3 to the 2k plus 11. And now we're doing a bit better, because this is the same as 9 times 3 to the 2k plus 11, and then we can make an adjustment. So this would give us 99 if we expanded it from 9 times 11. But we only have 11, so we need to take away 8 times 11, 88. So now we can say this is 9 times 3 to the 2k plus 11 minus 4 times 22. Why am I writing it in terms of 4? Because we want to show it's divisible by 4. So this bit here is divisible by 4 by the assumption. And this bit here has a factor of 4, so this is also divisible by 4. If we subtract two things that are divisible by 4, it's still divisible by 4. So therefore, the whole thing, let's say if 3 to the 2k plus 11 is divisible by 4, so is 3 to the 2k plus 1 plus 11. The statement is also true for n equals 1. So it is true for all n in the positive integers by induction. So this very long conclusion we write every single time, that's necessary. You have to do that. And this sort of explanation we've got here, you need that as well. Really, my answer is the kind of minimum that you would need to write. Not that there are many other ways you could flesh this out, but just to be clear, you have to write your answer very carefully for an induction question. So now we'll consider a different example. So now the question is prove n cubed minus 7n plus 9 is divisible by 3 for n a positive integer again. So this time the proof, we'll first do the base case as always. If n is 1, 1 cubed minus 7 times 1 plus 9 is 3, which is divisible by 3. So it's true for n equals 1. And then we'll assume it's true for n equals k, which means k cubed minus 7k plus 9, we're assuming to be divisible by 3. And then we'll consider k plus 1 cubed minus 7k plus 1 plus 9. And again, we'll employ the same strategy as last time to try and somehow rewrite this as something times as something that somehow in terms of k cubed minus 7k plus 9. So let's just expand this out. This is k cubed plus 3k squared plus 3k plus 1 minus 7k minus 7 add 9. And then this is equal to this is equal to k cubed plus 3k squared minus 4k plus 3. And then we can see we've got a k cubed minus 7k plus 9 kind of hiding in here somewhere. And we need to add 3k squared, add 3k, and take away 6 to make this work. And then this bit in red, this is divisible by 3 by the assumption, and the other bit is the same as 3 lots of k squared plus 2 plus k minus 2. So that's also divisible by 3. So the whole thing is divisible by 3. So then we can say, if the statement is true for n equals k, it is true for n equals k plus 1, and it is true for n equals 1, so it is true for all positive integers n by induction. And then we'll just see one last example, which is prove for all n in z plus 11 to the n plus 1 plus 12 to the 2n minus 1 is divisible by 133. So same as always, we start with the base case. If n is 1, 11 to the n plus 1 plus 12 to the 2n minus 1 is 11 squared, which is 121 plus 12, which is 133. So it's true for n equals 1, because 133 is divisible by itself. We'll then assume that the statement is true for n equals k, which means we're assuming 11 to the k plus 1 plus 12 to the 2k minus 1 is divisible by 133, and we'll show this implies it's true for n equals k plus 1. So we'll now consider 11 to the k plus 2 plus 12 to the 2k plus 1 minus 1, which is the same as 11 times 11 to the k plus 1 plus, and then if we so this is the same as 12 squared times 12 to the 2k minus 1, because we get an extra power of 2 of 12 when we expand out. So we can see that this, we want to write it in terms of 11 to the k plus 1 plus 12 to the 2k minus 1. We certainly have 11 lots of that. And then we have some extra stuff left. We have how much left? 12 squared minus 11 lots of 12 to the 2k minus 1. And then we see again this thing we had before, where this thing in red is, by the assumption, divisible by 133. And then this other bracket, well, what is 12 squared minus 11? It's 133, isn't it? This is 133. So, so certainly the second part is divisible by 133. So again, we've shown if it's true for n equals k, it's true for n equals k plus 1. So we can say, now we just make our conclusion. Therefore, it's true for n equals 1. And if it's true for n equals k, it is true for n equals k plus 1, so it is true for all n in the positive integers by induction. End of proof. And maybe I'll now tell you the answer to this question about the horse. I've lost it. Here we go. All horses are the same colour. The problem is, with the induction step, what happens if k is 1? So what if we consider 2 horses? Well, if we try and use our claimed proof of the induction step just for 2 horses, so if we just have these 2 yellow horses, well, no, we'll make them different colours too. If we have a yellow horse and a green horse like this, different colours, when we try and say, because it's true for all groups of horses of size 1, it's true for all groups of size 2. The problem is, this time the red and the blue groups we had before have no overlap. So we can't say these 2 are the same color as each other. So it is true that if it's true for all groups of size 5, it's true for all groups of size 6. But it doesn't, but the 1 implies 2 doesn't work. So it fails for n equals 2, and therefore the whole induction proof fails. So it's a nice example to illustrate possible failures of induction. Yeah, so we'll stop there.